Good morning and welcome to this next lecture. We were looking at frequency regimes, okay. M being my non-dimensional frequency, we were trying to see if the roots close to 1, okay, but just less than 1 were still perturbations. To the original roots. Similarly, we tried to see for frequency values very close to 0 if the roots were perturbations, okay. For values of m close to 1, we found the roots were perturbations to the uncoupled roots. So, we will call it still the light fluid loading regime, but that was not the case when m was order epsilon, okay. We could not balance the coupled dispersion equation. So, let us try this. Let us try m is equal to epsilon to the power beta n. I am putting n, but notionally n is equal to 1, okay. So, if beta moves towards 0, okay, m moves close to 1. If beta moves towards any positive value, 1 or any higher value, then m starts to move towards 0, okay. So, let us substitute this. If we do that, we have zeta to the power 4th minus 1 zeta square minus m square. Therefore, epsilon to the power twice beta n square to the power half minus epsilon into 1 minus beta over n. That has to be equal to 0, okay. If you recall, we had derived the physical significance of each of these terms. This had come from structural stiffness, this had come from structural inertia, this had come from fluid pressure, this from fluid compressibility, and this was denoting fluid inertia. Okay. Now you can see that when beta is 0, when beta equal to 0, okay, that means m is just near 1, okay, less than 1. Oh, let us number this, sorry, just number it 1, 2, 3, 4, 5, okay. So, 5 is the smallest, inertia is the smallest, fluid inertia is the smallest, okay. Next, as beta increases, that means m is starting to come down, okay. Fluid inertia starts to dominate, fluid inertia starts to dominate. I will denote it, start going up, and when m is less than equal to order epsilon, most significant fluid inertia most significant. Okay. At high frequencies, five is negligible. Negligible. Now, as beta goes up, fluid compressibility goes down. That means 4 goes down. Term 4 comes down. Which is seen from here. Okay. When 0 is less than beta is less than 1, okay, fluid inertia and compressibility are smaller than the other terms. Thus, at these intermediate frequencies, that is order epsilon less than m less than 1, the dynamics is governed or dominated by structural stiffness, which is 1, structural inertia, which is 2, and fluid pressure, which is 3. Okay. And within this range, as beta goes up, the fluid inertia starts to dominate and compressibility comes down. Okay. So let's try a further closer range, that is m is equal to order epsilon squared. We'll try this range. Okay. So we'll make this m as epsilon square n, again where n is an order 1 quantity. Okay. So we have our friendly coupled dispersion equation, zeta to the power 4th minus 1, zeta square minus m square to the power half minus epsilon by m, that's equal to 0. Okay. In addition, from some prior knowledge, I will replace zeta by epsilon to the power minus 1/5 xi. Okay, this is after some trial and error. This balance or idea has come. So if we now do this, what do I get? I get epsilon to the power minus 4/5 xi minus 1. Then I have epsilon to the power minus 2/5 xi square minus epsilon to the power 4th n square to the power half is equal to 1 by epsilon n. Okay, so let's take epsilon to the power minus 4/5 outside, then I get, I'm sorry, this to be 4th. Okay, then I get xi to the power 4th minus epsilon to the power 4/5. Okay, then I take epsilon to the power minus 2/5 out, so it comes out as epsilon to the power minus 1/5. Okay, and xi square, and inside I get epsilon to the power 4th plus 2/5 n square to the power half. That is equal to 1 over epsilon n. Okay, so if we look at this term and that term, we'll get epsilon to the power minus 1 xi 4th minus epsilon 4/5 xi square minus epsilon to the power 22/5 n square to the power half is equal to 1 over epsilon to the power n, and here also I have 1 over epsilon, so this goes. Okay, now as epsilon tends to 0, okay, you can see that structural inertia loses its dominance. Okay, so this is structural inertia, term 2, okay, which is term 2. Okay, and then fluid compressibility also starts to lose. This is the term, okay, 4. Okay, and the dynamics is largely governed by 1, which is structural stiffness, 2, sorry, not 2, by 3, term 3, which is fluid pressure, and 5, which is fluid inertia. Okay, so this region is heavy fluid loading. Okay, this region is called heavy fluid loading. Okay, now so this gives you an idea of how to use asymptotics, or the asymptotic method to play with order of the terms. Okay. Use asymptotic method to arrange order of the terms in order to examine physical influences. Okay. So this sort of a what shall I say, game can be played again and again to get finer and finer ideas about relative importance of these 5 terms. The next topic is farfield acoustic directivity. We have seen the uncoupled sound field. So we are going to look at the coupled sound field. Now if you recall, phi of x comma y was given by I omega f by twice pi b integral minus infinity to infinity e to the power of I kx minus gamma y dk by k fourth minus kp fourth gamma minus mu kp fourth. Now we are going to look at this or compute the integral using the method of stationary phase. It's an amazing technique where a function oscillates in some places of the range and does not oscillate in some places of the range. So the method, this method of stationary phase is essentially I have an integral of this form a to b, okay, f of omega e to the power I x h of omega d omega. Okay. Now this exponent, this term can be is a cos and sine, so it can be oscillatory, can be heavily oscillatory. Okay. For example, h of omega, I'll take the first, let's say, is equal to omega square minus omega, okay, or another example I will take is b, which is h2 of omega is equal to omega cube minus omega. Okay. For the moment we are taking an example for method of stationary phase which we will apply here. So for the moment this part, this expression I will consider to be a cosine, okay, for making life easy. Okay. So it's cosine of x h1 of omega in this case and cosine x h2 omega here in this case, which will go in here. Okay. Now these functions h1 omega and h2 omega, how do they look? they look like this. So h1 omega looks like this. So minus 1, 0, 1. Okay. So it goes through 0, this is 0, some value, whatever value is here, it goes through 0 at 0 and it goes through 0 at 1. Okay. The next function h2 of omega, which is cubic in omega, so it will go through 0 3 places at omega equal to 0, omega equal to minus 1 and omega equal to 1. So it looks like this. Okay, it looks like this. Now correspondingly if I plot the cos of h1 of omega, okay, it looks crazy. Okay, it looks like this here, and as we approach this minimum here, it will actually let me mark it somewhere. So it will come and it will slow down and it will start again going up. Okay. Similarly for this one here, if we plot, okay, so here is a maximum, here is a minimum. If we plot it, it will go oscillatory and then it will slow down. It will go oscillatory and then again slow down. Okay. So now the idea is, if we integrate over this omega range, okay, here or here, if we integrate, then these regions are highly oscillatory and they will cancel out. The neighboring regions cancel out, positives and negatives. The contribution will come mainly from this region where this phase factor had a minimum or a maximum. Okay. So here also this phase has a maximum here, it has a minimum over here, and here the function slows down in its oscillations. Here the function slows down in its oscillations. Everywhere else the oscillations cancel each other. So if you integrate, the contribution will come from here and here. That's the idea. That's the idea of the method of stationary phase. Okay. So now what is the statement? If you have a function like this, y of x is equal to integral minus infinity to infinity f of omega e to the power of I x h of omega d omega, if you have a function of this form, and so the oscillatory nature comes from this term, then right away, okay, y of x is equal to twice pi by x modulus of h double dash omega 0 to the power half f of omega 0 e to the power I x h omega 0 then plus or minus I pi by 4. Okay, the plus or minus is chosen as whether it's a maxima or a minima. Okay, so this is the answer. This is the answer. There is no more integral. So I'll show you an example using one of these functions that I have chosen. Okay. So consider this function here, which is y1 of x equal to integral minus infinity to infinity cos of x omega square minus omega d omega. Okay, this is an example. Okay, so if I use the method of stationary phase, I get an answer of 0.10764,101 etc. whatever. Okay, and I choose x equal to 100 and f of omega is 1 is equal to 1. Okay, so this is method of stationary phase answer. Then I use some software, say Maple software, to integrate numerically. So I'll show you the numerical values. Okay, so the omega limits and then integral value. So let's see, minus 0.6 to 0.6, I get 0.143844 so forth. Minus 1 to 1, I get 0.1045,276. Minus 2.0 to 2.0, I get 0.1048,164 etc. Minus 10 to 10, I get 0.1075082 etc. From minus 100 to 100, I get 0.10767,455 etc. Minus, speeding it up, minus 1000 to 1000, I get 0.1076314 etc. Okay, then minus 10,000 to 10,000, I get 0.107640544. So you can see, compare this with this value. So that's the method of stationary phase. Okay, so we are going to use this method to compute our acoustics integral. we are run out of time. So, I will stop here and continue next class. Thanks.